break, and I'll be back here at 3 o'clock. Center for Applied Energy Research of the University of Kentucky. Title is Activity Studies of Zirconia Superacid Catalysts. The speaker is S. Chokkakam, co-authors are Ram Srinivasan and Bert Davis.
Thank you. Thank you. So I'm going to talk on the activity studies of Zirconia superacid catalysts. I'm sure So basically, I'm going to talk a brief introduction on the superacids and sulfated zirconia preparation, characterization, results, and finally, I'm going to talk about the activity measurements on sulfated zirconia catalysts, the reaction profile of two optional reactions and two butanol reactions. According to Garrett's definition of minerals, any acid may be termed as superacid when its acidity is stronger than that of 100% sulfuric acid, whose HCl value is less than -7.9. So what are the types of solid superacids? Liquid acid mounted on suitable carriers as BFR, BFR composites and SB, F5 HS03, F6. So when these liquid acids are supported and suitable carriers, they act as a superacids. Combination of inorganics of like aluminum chloride, copper chloride, and aluminum chloride, copper sulfate. And also, recently, a couple of years from, sulfate and promoted metal oxide, such as sulfated zirconia, sulfate iron oxide, sulfated type TiO2, sulfated tin dioxide, which acts as a superacids. And also, metal promoted superacid, the sulfated zirconia are promoted by platinum like metals. Their performance and their selectivity improved well. And the well-known as Nafian H also acts as a superacid, and the well-known zeolites, example, Zirconia also come from the category. So these are some of the amide acidic functions of these acids. So which is raised from -10 to less than -20 for HFNSD approved by competitions. So as we have already mentioned in the first slide, metal oxides such as zirconia, TiO2, NaPePO4, and SnO2 are known as solid acids. However, the acidity of these oxides is remarkably enhanced in the addition of small amounts of sulfate. And these solid acids are very important in variety of industrially important catalytic processes. So it is also claimed in the literature that when the zirconia is sulfated, it exhibits superacidic character. And we will know, we'll discuss later how the acidic character is like. And finally, the superacidity of sulfate zirconia is considered to be generated by the interaction between the oxide and the sulfate ion with the surface of zirconia. So this model A structure has been ascertained by IR studies by the decrease in the bond between the SO bond and SO double bond. this sulfate, this kind of structure is only obtained when the zirconia sulfate, zirconium oxide is treated with SO3 only, but not when it is treated with SO2 or H2S. And this time, it is reported that in the literature, when sulfur is in highest oxidation state, that is +6, it exhibited superacidic character. This was reported by Chokkakam et al. Recently. What are the uses of this superacid? These catalysts, solid superacids, are very useful in the industrial process such as hydrocracking of heavy oils and isomerization of hydrocarbons, which leads to jet fuels and lubricants, and also hydroisomerization of long chain organophosphates, and esterification of various organic compounds, alkylation of aromatics, carbonylation reactions, and polymerization reactions, as well as acylation of aromatics. So what are the advantages of these solid superacids or the liquid superacids or what we have mentioned, HF and SBF series? So ease of separation and also reusability and high thermal stability and low cost, and also they are very good, very active even at low temperatures. We have started from the preparation of sulfate zirconia. So we have prepared the sulfate zirconia from zirconia dioxide gels. So the starting material zirconia is prepared from different precursor starting materials, zirconium oxynitride, zirconium tetrachloride, or zirconium sulfide, by distillation with the ammonium hydroxide at different pH values. So in this series, the zirconia is used from prepared from zirconium oxynitride by distillation with ammonia at pH 10.5, and these the resulting zirconium dioxide is calcined at 400 degrees and one is dry. So these two starting zirconium oxide gels are used for the adsorption of sulfate. So in a typical experiment, what we did, we took 10 grams of zirconia gel and immersed in a 60 ml of sulfuric acid with no concentration, and stir incubated for 2 hours and filter, wash it, to remove the physically absorbed sulfate. And those were wonderful explanations. The resulting sulfated zirconium samples were used for the character and activity for 2-octanol dehydration as well as 2-methanol dehydration reactor. So for this purpose, we use a fixed bed tubular reactor for hot reactor for reaction studies. This figure shows the adsorption of sulfate on the dried zirconia as a function of sulfuric acid once the infiltration is liquid. So as we know, as the concentration of sulfuric acid increases, the adsorption of sulfate also increases, and it appears that it is almost reached a saturation level, but it slightly increases with when the concentration of sulfuric acid increases. And the percentage of sulfate adsorption gradually decreases with the concentration of sulfate increases. This figure shows the adsorption of sulfate on the calcined zirconia, which is calcium number 400 degrees in A, and in the same case happens for this zirconia sample also. As the concentration of sulfate that increases, the adsorption in a sulfate adsorption increases, but it is almost saturates. can compare both the samples in this figure. As you see, as the sulfuric balance, the sulfuric acid concentration increases. On the calcium sample, it saturates, but in the lead sample, it is not saturated. It's a slight increase is there. This has been found because when the concentration of sulfuric acid in solution increases, part of zirconia is going into solution, maybe forming in a soluble like zirconium sulfate like soluble material. So it is actually dissolution like this occurring in the lead sample. So these samples are helped by measuring the surface area. This figure shows the surface area change, the sulfate, weight percent of sulfate absorbed per gram of zirconia. So as you know, that as the sulfate, as the weight percent of sulfate increases, the purity surface also increases and goes to a maximum, and with further increases in the sulfate absorption, indirectly the increase in the concentration of the potential sulfuric acid concentration. So it appears that there is a particular level, so the surface area is maximum. Now, coming to the reactions involved, 2-butanol dehydration as well as 2-octanol dehydration reactions. And I will not just mention what are the reactions going on. Here, when 2-butanol is dehydrated or dehydrated, you will get ketones. When it is dehydrated and its water is removed, it can form 1-butene or 6,000-butanes. In case of 2-octanol dehydration, similar things can be seen. When dehydrated, you get ketones. When the dehydration takes place, it can be 1-octene or 2-octene or the trans-octene or cis-octanes also, and also some more combinations also expected. So now coming to the reaction of butanol on the sulfated zirconia. So the dehydration of 2-butanol was carried at 140 degrees centigrade in a reactor. What we did, we passed the 2-butanol reactants through the catalyst that is a fixed fluoride of the butanol, and resulting products should be collected and analyzed by gas control. So this is the conversion of 2-butanol as a function of weight percent of sulfate. So now here you can see, as the weight percent of sulfate increases, the conversion is also very increasing at a different velocities of 2-butanol. But here you can see, if you extrapolate to 0% of sulfur, all match, intersecting on the y-axis at a definite value of the conversion. Here, what we assume that since we are decorating the zirconia gel by absorbing sulfate, so that means you are absorbing sulfuric acid, which is an acid catalyst for different dehydration reactions of butanol. So what we think that this is the activity of the sulfate or sulfuric acid salt on the zirconia. It is the true contribution of the sulfate or sulfuric acid contribution. And when we did very low, in order to find out that, we took 1% of sulfate and did a very low liquid or space velocity where the conversion is very low, because at that level the sulfate levels are very less. That's the reason we are not getting much activity. So, but in other cases, all are matching. So this really can say that this conversion will represent contribution from the sulfate epsilon. And also we have observed that the activity of the sulfated zirconia catalysts are very much dependent on the pre-treatment of the sulfated zirconia. So in order to find out these effects, we have treated this sulfated zirconia with the hydrogen, with oxygen, and in order to find what is the activity and selectivity of this catalyst. So we did for the 2-octanol hydrogen reaction. This figure shows the 2-octanol conversion as a function of time on the hydrogen treated zirconia sulfate. This sample is sulfated zirconia, starting metal 9% sulfated zirconia. So as you can see, as the time goes, the conversion is almost about less than 5%. But the selectivity for 1-octane is very high. So this was stable even we have tried for up to 100 degrees or so. The selectivity for 1-octane is constant. Whereas when you treat the same catalyst with oxygen, the activity and selectivity are just reversed. You can see here, as the time goes, the conversion of 2-octanol is gradually increases and almost stays about 99% conversion. But the selectivity for 1-octane is less than 5%. And here we get all kinds of other isomerization products like cis-octane, trans, as well as 2-octanes also formed. So this tells that the pre-treatment of sulfated zirconia is very important to predict what the activity of the catalyst. And the next precipitated from zirconium sulfate with ammonium hydroxide. So what is the, we wanted to know what is the real effect, what is happening when hydrogen, when you treat with hydrogen, the catalyst is not active but it's selective for one. And when you treat with oxygen, it is active but not selective. So really we wanted to know what is the role of sulfate, is the role of sulfate or something else. What is the station state of sulfur or what else. So in order to find out what we did, we precipitated the zirconia from zirconium sulfate and studied the effect of washings, how the washings could affect the activity and selectivity for 2-octanol dehydration reaction. When it is 2-wash, the activity is really about 60, about maybe a big condition is about 60%, and the selectivity is about 10%. When the washing times are increased, the activities came down to about 2%, and selectivity for 1-octane is gradually increased to 100%. So this also tells that there is something is associated with the nature of the sulfate and the catalyst. So in order to find out what is the effect of hydrogen treated, as we know in this previous slide, we have seen that when the zirconia is spread from zirconia sulfate, when it is 2-wash, the activity is about 60% and selectivity is 10%. But when we treat the same catalyst and in hydrogen, the conversion goes to below 2%, but the selectivity goes to 100%. So this also tells something about the nature of the sulfate program with zirconia. So, this is some literature. What is happening really in this catalyst? So, according to Chokkakam et al., the double bond nature of the complex is much stronger compared to that of the simple metal sulfate in the sulfated zirconia. Thus, the Lewis acid strength of zirconia of this group becomes remarkably stronger by the indirect effect of SO in the complex. If water molecules are present, the Lewis acid sites are converted to bronzes acid sites as shown in the graph. So in order to tell about this, we studied, we have took the sulfated zirconia. When we treat in hydrogen, the activity goes down and the selectivity for 1 octane increases. But in order to find out what is really happening, what we did, we took the catalyst to high temperatures, about 350, where the activity is considerably increased. We run that reaction for about 20 hours. Then again we brought the reaction temperature to 220, where other catalysts were studied. But for our understanding, what we found, the activity increased and the selectivity decreased. This shows that when the temperature of the reaction temperature is going up, the activity is increasing, and whatever the water molecules are formed, they are associating with these UV cells converting to brown cells and acid sites, and thereby the acid activity is increasing. So to conclude, the BET surface area of the sulfated Zirconia samples depend on the concentration of sulfuric acid in solution. And the activity and selectivity of sulfated Zirconia depends on the pretreatment. Attitude treated samples show low activity for alcohol conversions, but are selective for non-active. Oxygen treated samples are highly active for alcohol conversion reactions. And finally, the activity and selectivity of sulfated Zirconia is associated with the oxidation state or chemical